Hi gents, welcome to your first applied maths class together. Bit of a strange one, staring into a screen instead of you guys being in front of me, but this apparently is where we're at the moment. I hope you're all keeping well. I hope your families are all well. I hope everybody back in Spain, all your friends are well. I know things are tough there. But look, this is the way we are probably for quite a while, if I was to make a guess. But look, we will do the best that we can. Today's video is just going to be a very short one. It's really just a proof of concept, just to see will this work or won't this work. This could be good. This could be a bit of a disaster. Just to talk about the format. Format is recorded video, obviously, since you're watching this. I just think that is better than doing some sort of live class where, I don't know, this has advantages. You can pause me, you can try the question yourself, you can go back and look at it, rewind and play it again. There's all sorts of advantages to having a live class. I'm assuming that you're gonna prefer this format, but obviously do let me know if you prefer a live class or something like that. But yeah, I would appreciate feedback on this. So maybe nominate one person between you just to drop me an email and say yes, we like this format, or no, we prefer to do it a different way. Okay. With that said, we'll just kick straight into it. As I say, it's going to be a short one. We'll just do one question from 4C, just to see whether this works out nicely or not. I'm assuming that you know 4B off by heart, because you will need that. You'll need that for this. So it's page 55. So you should just take that out in front of you. It says two cars P and Q travel towards a junction. Junction is called O, on roads which are at right angles to one another. Okay. So we've got right angles. Let's see if I can manage to actually draw this. Might not be terrible. Okay, that's not the worst thing I've done. Okay, that's approximately at right angles. Okay, what do we know? We know that P is traveling north at 12 meters per second. Okay, so that did not work, but maybe this will. And we'll turn that red. Okay, P is traveling north, so it's already at the south, and it's going north. It's traveling at 12 meters per second. And what is the distance? It is 60 meters from O. O is obviously the origin, and so that distance there is 60 meters. Thereabouts. What do we have? We have Q is traveling east, so it is currently over in the west. So which one is this? This is Q. It's traveling at 5 meters per second, and its distance is, let's see, 51 meters from O. Okay, so that distance there, all the way, is 51 meters. Okay. The real trick with this, if you remember the last one, 4B, what we were saying was we always it was always the case that one particle was directly east or west. So what we want to do here, the trick to this one is you want to actually just allow things to develop. Okay, we know that P is traveling north. It's doing 12 meters every second, and it's got to go 60 meters before it hits at O. So what we should do is we should actually let that happen. Okay, so let's let that travel. Obviously, that is going to take 5 seconds. That's going to be important. So what we'll do is we'll let time go on so that at O, we'll let P actually arrive at O. We know that this is going to happen after 5 seconds. Obviously, if it's going 12 meters per second, it's going to cover 60 meters inside that time. We can use our little triangle just to say that. Time is distance divided by speed. Sorry to be so obvious on it, but we may as well just write it out here. Distance 60, speed 12, time 5 seconds. And what's also important is to find out, well, where is Q at this particular moment? So Q is going to be traveling 4 or 5 seconds at 5 meters per second. So it's going to have traveled 25 meters. It's traveling east. So if it does travel 25 meters, it is going to be, not to scale, it's going to be 26 meters away. Okay, and essentially what's happened now is we've turned it into a problem that we've done before. Okay, it turns into just a problem that we've already completed. It now becomes a question like 4b. So we may as well just do it out like we would any of the other ones. We'll have less offensive color here. We'll pick green and go from there. Okay, so let's see, things that we can say for sure. We can say these are our displacement vectors. Okay, probably don't even need to write these down, but anyway, this is minus 26i, that's where Q is, and no J's. And P is sitting at obviously 0i plus 0j. Now these bits are important. What's the velocity vector of Q, velocity vector of P? Okay, Q we already knew was traveling east, so it was moving over 5 i's and not moving over any j's, and P was on the way up, wasn't going left to right, so no i's, and it was on the way up 12 j's. Now if we actually answer some of the questions, we've actually already done it. Number 1 says how long does it take P to reach O? Well, that one, part 1, 5 seconds, simple. How far will O be? How far from O will Q be? We actually already answered that as well. Just anticipating what the question was going to ask. Maybe we should have read it first, who knows. Find the velocity of Q relative to P. Okay, so we will do that thing here. The velocity of Q relative to P, written like that, and you guys already know, excuse me, that it is velocity of Q minus velocity of P. So that's going to be 5i, and then we take away velocity of P, so minus 12j. You will already know what that velocity is. Okay, we know that that means that it is traveling at 13 meters per second. How do we know that? Pythagoras' theorem. You obviously know the 5, 12, and 13 triangle. So that one you would just already have there in your mind. So find the velocity of Q relative to P. We've already answered that. That's going to be part 3 right there. Okay, there is a fourth part. Calculate the shortest distance between the cars in subsequent motion. All right. So if we go over to our diagram, okay, if we go over to that, and what we're going to do is we're going to fix P, and we're going to see what does it look like Q is doing relative to P. So for this, I'm just going to zoom in on our diagram here just so we can see it. And we know that from P's perspective, it looks like Q is going to be moving over 5 and moving down 12. So moving to the right 5, moving down 12. So, you know, as far as it's concerned, it looks like it's doing something like that. Okay, something like that. What we're interested in is what is that distance there, what is the shortest distance between the two things. Before we get there, let's just figure some stuff out. Okay, first thing that you want to do is we want to talk about what is that angle theta there. It's important to have that one. So I might actually just make this a little bit smaller so that we can see everything nicely here. Okay, so what is theta? Well, we know that this length here is 5. We know that that length there is 12. Don't write down minus 12. We know, of course, that it is going down 12, but that's fine. Based on that, what we can say is that, not the sine, but we can say that the tan of theta is equal to 12 over 5. And we can also write down what's sine theta and what's cos theta. Obviously, that hypotenuse is going to be 13. So if you wanted to write down what is the sine of theta here, we would be able to say that it is opposite over hypotenuse. So 12 over 13. We'd also be able to say that cos theta, I don't think that's going to come into it, but I'll just write it in anyway, just in case it does come into it, is going to be 5 over 13. Okay, that bit's all important. With that done, I'll take out the 5 and the 12 now, and I'll also take out that thing there, and of course I've gone and killed our line that we were relying on to begin with. Let's try and get it back. Okay, roughly like that. Okay, I'm sure we'll change color again, just hopefully make this nice and clear. Okay, the actual line we're looking for is this one here. I'm going to call that thing D. Okay, we know theta already, or at least we don't know theta, but we know about tan theta, sine theta, cos theta, and theta hasn't changed there from that one. So what can we actually say? In terms of theta, D is the opposite, and the hypotenuse is 26. So I'm just going to write it up here at the top. What we will say is opposite and hypotenuse, that is sine. As we were saying, that's the one that we're probably going to have to use. Sine theta is equal to opposite, which is D, over the hypotenuse, which is 26. And we already know what sine theta is. It's right there, so we can just put that in. 12 over 13 is equal to D over 26. Multiply both sides by 26. We have 26 times 12 over 13. 13 divides in twice, so we get our answer of D equals 24. I think they were meters, and there you go. That is the shortest distance between the two. So that there is our answer to number 4, and we're happy enough with that, and that actually answers the whole question. So part 4 is equal to 24 meters. Okay, what to take from the video? Hopefully you've found the format okay, that you can actually follow the whole thing as we go along. But aside from the video, just the question, what's the plan? The plan is simply take the initial conditions and just fast forward until it reaches a moment like one that we've dealt with before. We want where something is precisely left or right, east or west of the other particle. So they're not like that at the moment, but if you leave them 5 seconds, they will be. So let the whole situation run on 5 seconds, and then you'll be able to solve it in that way. Next video, we'll go on to things where it's more complicated, where they're not going on a road which is at right angles, but maybe a different angle to each other, and we'll solve from there. Okay, gents, I hope this was useful, and I'll talk to you soon. Take care. All the best.